Section 1. Prediction versus forecasting, apples and oranges in the world of data. Prediction and forecasting are often used interchangeably. However, they are distinct concepts. Understanding this difference is crucial for effective data analysis. Prediction is about estimating an unknown outcome. This could be anything from a customer's likelihood to purchase a product to the outcome of an election. Forecasting, on the other hand, focuses on projecting future trends based on historical data. We use it to anticipate things like stock prices or weather patterns. Think of it this way: predicting is like determining the winner of a single coin toss. We analyze factors like the coin's weight and the force of the flip. Forecasting, however, is more like predicting the overall distribution of heads and tails over 1,000 tosses. We rely on historical data and trends for forecasting. Prediction often deals with individual events or behaviors. Both prediction and forecasting are powerful tools. They help us make informed decisions. Understanding their differences allows us to apply them appropriately. This leads to more accurate and insightful results. Whether we're analyzing customer behavior or predicting election results, using the right tool is key. This nuanced understanding is fundamental to data analysis. Section 2. The prediction life cycle. A journey from raw data to actionable insights. The prediction process is a journey. It transforms raw data into valuable insights. This journey typically involves several key steps. Understanding each step is crucial for building effective prediction models. It all starts with understanding the business problem. We need to define the specific question we're trying to answer. This could be anything from reducing customer churn to optimizing marketing campaigns. Next comes data collection. We gather all relevant data. This data could be historical sales figures, customer demographics, or website traffic patterns. The more data we have, the better our model will be. Once we have our data, we need to prepare it for analysis. This involves cleaning the data. We remove errors, inconsistencies, and missing values. We also need to format the data. This ensures compatibility with our chosen analytical tools. Now we choose the right prediction model. The choice depends on the specific problem. We might use a decision tree, a neural network, or a regression model. Each model has its strengths and weaknesses. Selecting the right one is crucial. After choosing the model, we train it using our prepared data. This allows the model to learn patterns and relationships within the data. Section 3. Regression analysis, unveiling relationships in the sea of data. Regression analysis is a powerful statistical method. It helps us understand relationships between variables. It's like a detective's magnifying glass, revealing hidden connections in data. Imagine we want to understand how advertising spend impacts sales. Regression analysis can help us quantify this relationship. It tells us how much sales increase or decrease for every dollar spent on advertising. Regression analysis has a wide range of applications. Businesses use it for price optimization and demand forecasting. In healthcare, it helps predict patient readmission rates. Social scientists use it to study the impact of social policies. The versatility of regression analysis makes it a cornerstone of data science. It's about finding the line of best fit. This line represents the relationship between variables. By understanding this relationship, we can make predictions about future outcomes. For example, we can predict future sales based on advertising spend. This predictive power makes regression analysis invaluable. It moves us from simply observing data to understanding the forces driving it. This understanding is key for making informed decisions. Whether we're optimizing pricing strategies or predicting disease outbreaks, regression analysis provides the tools to do so effectively. This makes it an essential tool in any data analyst's toolkit. Section 4. Machine learning versus statistical regression. Two sides of the same coin. Machine learning and statistical regression both use regression analysis. However, they approach it from different angles. Understanding these differences is key to choosing the best approach for a given problem. Statistical regression relies on strong assumptions about the data. This includes the distribution of the data and the relationship between variables. It's like using a precise map. This map works well if we follow the predefined routes. Machine learning, on the other hand, is more flexible. It learns patterns from the data without relying on strict assumptions. It's like using a compass and a set of general directions. We can explore different paths and adapt to unexpected terrain. Machine learning excels in complex scenarios. These situations involve large data sets with intricate relationships. Statistical regression is more suitable when we have a good understanding of the underlying data structure. Both approaches have their strengths and weaknesses. Choosing the right one depends on the specific problem and the available data. Sometimes, combining both approaches yields the best results. This hybrid approach leverages the strengths of each method. It offers a more comprehensive understanding of the data. Section 5. Simple linear regression. Finding order in the chaos. Simple linear regression is the most basic form of regression analysis. It examines the relationship between two variables. One is the independent variable, which influences the other. The other is the dependent variable, which is the outcome we're trying to predict. Think of it like studying the relationship between hours of study and exam scores. Hours of study is our independent variable. Exam score is our dependent variable. Simple linear regression aims to find the best fitting straight line through the data points. This line represents the linear relationship between the variables. The slope of the line tells us how much the dependent variable changes for every unit change in the independent variable. A steeper slope indicates a stronger relationship. The intercept tells us the value of the dependent variable when the independent variable is 0. Simple linear regression is easy to understand and implement. It provides a good starting point for exploring relationships between variables. However, it's important to remember that it assumes a linear relationship. This assumption might not hold true in all situations. In such cases, other types of regression might be more appropriate. Section 6. Multiple linear regression, juggling more variables. Multiple linear regression expands on simple linear regression. It incorporates multiple independent variables to predict a single dependent variable. This allows us to model more complex relationships. Imagine trying to predict house prices. We can't just consider the size of the house. We need to factor in location, number of bedrooms, and other variables. Multiple linear regression allows us to do just that. Each independent variable has its own coefficient. These coefficients indicate the influence of each variable on the dependent variable. For example, location might have a larger coefficient than the number of bedrooms. This suggests that location has a stronger influence on house prices. Multiple linear regression helps us untangle the web of relationships between variables. It provides a more nuanced understanding of how different factors contribute to the outcome. However, adding more variables can also complicate the model. It's important to select relevant variables. Including too many variables can lead to overfitting. Overfitting occurs when the model becomes too specific to the training data. This reduces its ability to generalize to new data. Section 7. Nonlinear and polynomial regression. Embracing the curves of life. Not all relationships are linear. Sometimes a curved line better represents the relationship between variables. This is where nonlinear and polynomial regression come in. Nonlinear regression encompasses a wide range of models. These models capture nonlinear relationships. Polynomial regression is a specific type of nonlinear regression. It uses polynomial functions to model the relationship between variables. Imagine studying the relationship between temperature and plant growth. At low temperatures, plant growth might be slow. Growth might peak at a certain temperature. Beyond that, growth might decline as temperatures become too high. This relationship is best represented by a curve, not a straight line. Nonlinear and polynomial regression allow us to model these curved relationships. This provides a more accurate representation of the real world. However, these models are more complex than linear regression. They require a deeper understanding of the underlying mathematical concepts. Choosing the right nonlinear model can be challenging. It often involves trial and error. Despite these challenges, nonlinear and polynomial regression are essential tools. They allow us to model a wider range of phenomena. This expands our analytical capabilities. Section 8, Regression Analysis in Data Analytics, a cornerstone for decision-making. Regression analysis is an essential tool in data analytics. It helps us understand and predict the world around us. Its applications are vast and constantly evolving. Businesses use regression analysis to optimize pricing, forecast sales, and understand customer behavior. Healthcare professionals use it to predict patient outcomes, optimize resource allocation, and develop new treatments. Financial analysts rely on regression analysis to model investment risks, predict market trends, and make informed investment decisions. In the age of big data, regression analysis has become even more critical. We have access to unprecedented amounts of data. Regression analysis helps us make sense of this data. It extracts meaningful insights. These insights drive better decision-making. Whether we're predicting customer churn or forecasting economic growth, regression analysis provides the tools we need. Understanding the different types of regression is crucial. This allows us to choose the right approach for each problem. As data continues to proliferate, regression analysis will remain a cornerstone of data analytics. Its ability to uncover hidden relationships and predict future outcomes will continue to shape our understanding of the world. This makes it an indispensable tool for anyone looking to make sense of the data-driven world around us.